Hello and welcome to the second kind of segment here. So we're going to look at single slit diffraction now. All right. So single slit diffraction, just as a reminder, here are just the plane waves that are generated. We talked about this in the grade 11 course. We reviewed it earlier in this one. That when plane waves strike a single slit, they fan out or diffract in that fashion. And there are a couple of factors. All right. So diffraction factors. What affects the amount of diffraction? So there are three factors, and hopefully someone in there is yelling out the answers here. We know that width of slit is one, because the second one that's kind of tied to it, and people argue maybe there's only two real factors here, but I do break it into the three. Width of slit and the wavelength, because we talked earlier that if the wavelength and slit are the closer they are, then the greater the dispersion factor. So I mean, they're kind of one and the same, but I'm going to separate them. And then finally, the third one is our frequency. So there are three factors that kind of affect our diffraction. So moving along, Huygens. Remember, Huygens was the one that debated Newton as to whether wave traveled as a particle or as a wave. So Huygens, again, he's passed away before realizing or being recognized for his correct research. So one of the keys for his kind of debate in terms of light being a wave, it was Huygens' principle. And it basically states that every point on the wavefront is in fact a tiny point source. And that point source creates its own little wavelets, and the wavefront is then created by those tons of wavefronts creating a uniform or a linear or a curved front. So to put it more simple, if I was to create a curved front with a bunch of point sources like that, and each of those point sources they made their own little circular wave front so that each one acts like a point source. Those point sources overlap. So there's an infinite number of them. So if I was to draw more of these wave fronts in between here, you'll notice that basically the tangent is created, and there's where that wave front emanates from. Okay. Similarly, with a straight wave front, you have your series of point sources. So Huygens said that each time you draw a plane wave, like I did on this page, so I drew plane waves here, he said the whole principle behind plane waves existing is that each of those plane waves have a whole bunch of little point sources, and we know that point sources create circular pattern. And again, if there's an infinite number of them and they overlap, what happens is those circular wave fronts create a uniform wave front. Okay, so there is Huygens' principle, something that I would definitely consider putting on an assessment and being able to explain how he believed the plane waves were created or propagated, I guess, within a medium. Okay, so diffraction through a single slit. You've seen maybe before in your house, light creeping through a small crack in the door, and what's it do? It kind of spreads out, all right? And so light, when it goes through that slit, it does spread out. So we want to talk about specifically how does it spread out. So single slit diffraction, very similar to double slit, Young's double slit that we've already looked at. You've done some hands-on stuff with it. The dark and bright bands are not equally spaced. So if you recall, every time we measured the distance between bright and dark bands, they were the same. It's not true for a single slit spacing, and we'll talk about the why, or I'll show you the math on the why on that. And the intensity of the bands are not equal. So in terms of intensity, if you recall, the double slit, I'll do this off to the side here, double slit intensity, each band had the same width and the same brightness, and so on and so forth. So if I was to draw a graph with intensity on the y-axis and then some distance x there, we would find that the intensity for each band, because it's equally bright, the intensity would be the same for every band. So that is my intensity. So each of those represents a bright band. Now, if you look at my example here, and this comes from, if you look on my website where you found the videos, there are website applets. If you go to this website, and I encourage you to try it, it gives you an opportunity to play with wavelength and frequency and distance from the screen, all the factors involved in that single slit. So if I superimpose a similar axis on this, you can see that the central band is much, much wider and much, much brighter than the rest of the screen. So like I said, if you want to pause the video now and try that applet, it doesn't take long. It kind of helps you visualize what's going on. So that central band is really wide and bright. And then you'll see there is symmetry, but these outer ones not quite as bright. And then these ones on the outside are getting dimmer and dimmer. So in terms of intensity, we have a very high intensity in that central band. And then as we move out, our intensity is decreasing. And anywhere that we have a dark band, we have virtually zero intensity. So this is what the intensity graph would look like for a single slit diffraction. All right, so that's central band. So if you compare the two, when you're looking at Young's double slit versus single slit, significantly different. All right, we call this band in the middle here our central maxima. We're going to talk about how it's developed and why it's like this, because the double slit, we showed you that we had constructive interference, and the two slits supported that. Now what happens when you only have a single slit? So, got a couple of cases here. First one is, and I've added some lines on here. You can just put sketching some dashed lines. That's my central line. Let's look at the light rays. The angle is 0. So that means that the light waves pass through. I'm going to try to do 6 light waves for each drawing here. If they pass through at 0 degrees, then all of them are staying in phase. They're going to strike the middle, and that's why we get that central maxima. So forms the central maxima. So these are the light waves that get through the slit uninfluenced or unaffected. So remember, single slit, we kind of talked about light goes through a slit. It's like putting a whole bunch of people through the door. Some are going to get through all right. Some are going to get kind of flung out sideways. So what about the ones that get flung out sideways or on an angle? So when theta is not equal to 0. So the angle we're really measuring here is, and maybe I'll leave that for a second. Let's draw your 6 light rays again. So you want to do 3 below the central line and 3 above. And they should be extended right back here. Try that one more time here. See if I can get it to work or draw it out properly. Oops. So light ray, as best you can. All right. So here we are. Now, quick geometry lesson. Okay. So there's the angle theta that we're measuring. If I'm to create, let's use blue here. That distance there is the width of the slit. This distance from here to here is going to be our delta L. So it's going to be how much further did that outside one have to travel than one of the inside ones. So when you do your geometry here, you're going to find that, quite simply, that this theta then becomes this theta down here, or that angle inside. And I'm just going to temporarily highlight it, this triangle right here. So we have a right angle triangle. That theta transfers in there. Okay, and the geometry just comes from opposite angle theorem, some of the angles being 90 degrees. So I can show that to you in class if you're curious as to why the angle works out that way. But for now, for the lesson part of it, you can go with just the belief that I'm actually not lying to you. Okay, so let's talk about the delta L. So over here, I said for the first situation, my delta L is going to equal 1 full wavelength. So what does that mean? Well, that means that if that has traveled one full wavelength on the outside, then the inside one here has traveled half a wavelength because of symmetry. You're halfway through the triangle. All right, so that distance there has to be lambda over 2, and that comes from similar triangles. All right, that light wave's in the middle. So what does that mean? So that means that I'll call this light wave number 1, the one on the outside, and I'm going to compare it to light wave number 2, the one that's traveled half as far. What does that mean for the two? Well, if light wave number 1 has done one full cycle, so let's say all the light waves hit the opening as a crest, so it means that this one's done one full cycle and it's ready to continue on as a crest. The one in the middle has only had not the chance to go half a cycle, which means that it's going to be starting as a trough. So what we find is the light waves 1 and 2, if we compare them, compare 1 and 2, if delta L is equal to lambda, then 1 and 2 cancel each other out, because one's going to be a trough, one's going to be a crest. And if we did it proportionally as you move through, that's why I had you draw 6 lines, it would be true mathematically that each one's traveled a proportional amount to create that cancellation, cancel out, or we call this destructive interference. Destructive interference. So that's why we get our first dark band, is because of that mathematical relationship. All right. So then if we move on to the next slide here, and we talk about it being 3 lambda over 2 our delta L. So again, you can go ahead and draw, or try to draw, your 6 light rays as best you can. And now, that distance from here to here, our delta L is now 3/2 lambda. So what's going to happen is we're going to divide this triangle, or this width here, into halves. So we're going to have 3/2. So at this point here, we're going to have 1 lambda, and then right here, see here, we go down, so right here would be lambda over 2. So I'm just breaking the triangle up proportionally. All right, so if this is the full triangle, that's 1.5, then we have 1 lambda and half lambda. So I'm just breaking it into 3 similar little triangles. If we do that, in that case then, just the way the symmetry works here, we find that, so what we find is that what we have is partial destructive interference. However, it's the ones that exist down here. So I'm just trying to pick the right kind of color here. So let's look at the lambda. The lambda, if it did one full cycle and started as a crest, that means it's going to go to the starting line entering as a crest. Lambda by 2 has only gone part of a cycle, and it's going to be a trough. So what happens if I have, I'm going to number them 1, 2, and 3. If you compare 2 and 3, so if our delta L was 3/2 lambda, 2 and 3 cancel out. Or the bottom 2/3 of the rays will cancel. But, so if that's the case, then these guys cancel each other out. Bottom 2/3, we still have the top, and you don't want to maybe cross that out, but that top third, but the top third continues. And I'll finish this up in the final video.